Photocycloadditions. In photocycloadditions, olefins uh, involve in additions with the different olefins, usually concerted additions. Both the excited state and the ground state retain stereochemistry. That means uh, here, this is the excited state olefin, and this one will be the ground state olefin. The ground state olefin is cis. That means in the product, cis configuration of the ground state reactant is retained. In the product, the excited state of the reactant stereochemistry is retained. Of course, this is not, it does not show geometrical isomerism, but this shows geometrical isomerism, more particularly 6. And here, both the CH3 groups are on same side. Here also, both the group CH3 groups are on the same side. Right. I will go to the next slide. In the next slide, I am taking few more examples. So here, a singlet one. And here also, this olefin is a ground state one, and this olefin is a excited state one. Then on irradiation, lambda max of the still beam, cis still beam, 2 pi cycloaddition forming a cyclobutane derivative. The stereochemistry of still beam is cis, that is here cis. And this does not exhibit stereochemistry because all are identical groups. And then here I am taking cis1 react with the cis1. And here there is a possibility of forming a two products. So what are the two products? You can observe that the phenyl groups are on the same side and methyl groups are on the same side. This is one isomer. Another isomer is if the CH3 groups are down, then it will be another isomer. That means mixture of two products is obtained when we are taking a two reactant of cis or trans one. In the previous one, one is a geometrical isomer, other one is non-geometrical isomer. But in these two, both the reactants are geometrical isomers, and that's the reason two products are obtained. With this, I will go to the next slide. Here I am taking a trans steel beam one. So trans steel beam one react dihydropyran. This is the dihydropyran. Usually, this dihydropyran is used as a protecting group for hydroxy 1, and this will undergo 2 pi cycloaddition. So forming a two product, one is exo, another one is endo. This is the endo product, and this will be the exo product. And this one is means reaction is irradiated at the 290 nanometer. Okay. And 290 nanometer is lambda max of the steel beam. So here I'm taking two strands product. One is fumaric ester. Another one is steel beam. So this are irradiated with the 290 nanometer. 290 nanometer is the lambda max of the steel beam. So it is observed that two product. You can observe that here the retention of trans steel beam configuration here. That means one is P9 above, another is P9 is down. And this fumarate one, COO ester here, COO ester here. That means in this isomer, retention of configuration with respect to steel beam as well as the fumarate. Here also retention of configuration, but orientation of the steel beam, orientation of the fumarate is different here. That's only the difference. Then here we are taking one geometrical isomerism, other non-symmetrical isomerism. Here also possible to get two product. Here, the two product is because of the steel beam orientation. So in this one, retention of the steel beam configuration. Here, orientation of the steel beam in different way to form a two different product. Then I will go to the next slide. Here I am taking the geometrical isomerism of olefins or cis-trans isomerism. So olefins or cis-trans isomerism readily takes place under photochemical condition, but not the thermal condition. Thermal condition, cis-trans isomerism is not possible, but in photochemical condition, it's possible. Geometrical or cis-trans isomerism is excited state isomerism. That means cis and trans isomerization takes place in the excited state. In cis-trans isomerism, whether the reaction started with either, that means if the reaction is started with cis, trans and cis will be the product. If the reaction is started with the trans, cis and trans will be the product. That means composition constant. That means 20, 30, 30, 40, 60, 40, 70, 30, a composition product is forming. So here I am taking an example. So cis is taken. So this on irradiation, it will give you the 20% transfer. But what it means, it means that it will be in equilibrium with the cis and trans, 20% trans and remaining 80% cis. So here I am taking the trans one is gets converted into 80% cis. What it means? It means that on photochemical irradiation, cis will be the major product. Then I'm taking one more example. Again, a cis steel beam. The lambda max of the cis steel beam is 290. Trans steel beam, the lambda max is 295. So when trans steel beam is irradiated at 313 nanometer, a trans one is converted into cis one of 93%. A cis one, when it is irradiated with the 313 nanometer, only 7% trans is obtained. This indicates that photochemically, cis one will be the major one. That means trans can be converted into cis. Cis conversion to trans is only a little less percentage. I will go to the next slide. And here I'm taking the theory. What is the theory behind the cis-trans tautomerism? Here you need to remember the two things. One is direct irradiation. So direct irradiation of the olefins, it undergoes cis-trans isomerization. So in this direct irradiation, singlet excited state is the key component. So let's take a cis olefin here and irradiation, direct irradiation. It will give you the vertical singlet excited state. So this vertical singlet excited state is converted into non-vertical singlet excited state. Similarly, if you are taking with the trans olefin, this on irradiation, it will give you the vertical singlet excited state. Vertical singlet excited state will convert it into non-vertical singlet excited state. So similar to your previous knowledge, what is that? Any compound on irradiation will give you the singlet will convert it into triplet. But in the case of olefin, we are using the two different terminology. The two terminologies are vertical singlet excited state. This is nothing but a singlet only. Non-vertical singlet excited state. This is something like similar to the triplet one. What is important here? The non-vertical singlet excited state is obtained when a compound is irradiated non-vertically. That means here there will be a change of here there will be a change of geometry. That means olefin in the vertical singlet excited state, geometry of the ground state and the excited state is similar, but olefin ground state and the non-vertical singlet excited states are different. That's what you need to remember. This non-vertical singlet excited state will give you the mixture of cis and trans product. This is the theory behind the cis-trans isomerism. This only we are taking few example and explaining it in further slides. And I will go to the next slide. In this next slide, whatever I explained here in terms of words, vertical singlet excited state, the geometry is same as the ground state. Non-vertical singlet excited state, the geometry differ from the ground state, neither cis or nor trans one. And you can remember that with respect to non-vertical singlet excited state, decomposition or distribution of non-vertical singlet excited state produce equal amounts of cis and trans product. And one more thing you can remember, non-vertical singlet excited state energy lesser compared to the vertical singlet energy. So this is again singlet means ground state, vertical singlet excited state, and non-vertical singlet excited state. That means here there is a change in geometry, and here vertical singlet excited state. And what is the difference between this ground state and this ground state? This ground state is cis, this ground state is trans. That's the only difference. Identical intermediate, the intermediate is non-vertical singlet excited state. This will give you mixture of trans and cis product. I will go to the next slide. In the next slide, I'm taking here it is explained in terms of orbital. Okay, singlet excited state, vertical singlet excited state, a 90-degree rotation. This is 90-degree rotation forming a non-vertical singlet excited state. Here starting material is cis, but here starting material is trans. It is in ground state. On irradiation, it will give you the vertical singlet excited state. This on 90-degree rotation, it will give you the non-vertical singlet excited state. This will give you the equal ratio or equal composition of cis and trans product. And with this, I will go to the next slide. So you can remember that on direct irradiation, singlet will be the product. On if we are using triplet irradiation in presence of triplet sensor, then there is a possibility of getting triplet one. So cis olefin on irradiation with the triplet sensitizer, it will give you the vertical excited vertical triplet excited state. There is a terminology difference from the singlet and triplet. Here, vertical triplet excited state. This vertical triplet excited state on 90-degree rotation will give you the non-vertical triplet excited state. Similarly, this compound is obtained from the trans olefin. Trans olefin on irradiation with the triplet sensitizer, it will give you the vertical triplet excited state. This on 90-degree rotation will give you the non-vertical triplet excited state. So this will give you the equal mixture of equal composition of cis and trans isomers. So I will, with this, I will go to the photochemistry of the conjugated olefin. So conjugated olefins means a double bond, single bond, double bond containing compounds are called conjugated olefins. You can observe that in the cis one, because of the substituent, there will be a steric interest. That is the reason thermodynamically trans will be more stable compared to the cis one because of the steric interest. And this is again a continuation of mechanism of triplet means what you call when we are using triplet sensitizer for the excitation of the olefin, it will give you the non-vertical triplet excited state. This will give you the mixture of cis and trans product. Then here I am taking example ground state one, excited state one, but cis one only less amount of the trans product is possible, but not the more quantity. Cis trans can be converted into cis in presence of what you call light photochemical reaction. With this, I think this example we discussed earlier, more particularly when we are discussing about the butadiene. So this butadiene on irradiation with the singlet excited state. So this we discussed under the heading of singlet excited state products and the triplet excited state product. So in the singlet excited products, only the cyclization occurs with the 10% of dimer, whereas in the triplet excited state, it will give you the dimerized product. So in addition to the dimerized product, there is also a cyclization product. This we discussed earlier, but now we will discuss its mechanism also. Now we will discuss its mechanism also. Here, bicyclo. So this is a butadiene. You know that this pi bond, if it undergoes homolytic cleavage, one radical here, one radical here. This pi bond, if it undergoes homolytic cleavage, this here radical. So that we will tell it in terms of electron, in terms of singlet, in terms of triplet. Okay. So then what will happen? Cyclization between this electron and this electron and this electron, forming a transition state like this and forming a bicyclic compound. So similarly, if it undergoes cyclization, then it will form a transition state like this and later on product like this. And then similarly, a triplet, these two are related to the singlet excited state. But when it comes to a triplet excited state, the dimerization occurs. That means butadiene irradiation in presence of triplet sensitizer, dimerized products are obtained. In addition to the dimerized product, a cyclized product also obtained. So here I am taking the mechanism. Look here, butadiene cis-1 I am taking 5% one and trans one 95%. Why? Because here steric hindrance is there, so that's the reason it is unstable. Here there is no steric hindrance and it is the stable one. And this is irradiated in presence of triplet sensitizer, so forming a dimerized key intermediates. And you know that this pi bond and this pi bond undergo excitation. In the excitation, forming a two things. What is the two things? This is the singlet one and this is the triplet one. So triplet excited state olefin react to the singlet olefin excited state. You can observe that these two electrons are opposite direction. So there is a bond formation. Then you can observe that here